Spelling distance treats names as characters, not sounds. Metaphone with jellyfish creates phonetic keys, so pronunciation variants become searchable before a similarity re-rank. You'll learn how the pieces fit into a workflow that finds sound-based name candidates and re-ranks them by spelling similarity. I'm Professor Pi, teaching search and IR with simple Python. Names break search in two ways. First, people type different spellings for the same spoken name. Second, databases store fixed strings. A raw edit distance check either misses Stephen versus Stephen or returns too many unrelated near misses. That cuts recall and wastes time ranking candidates that shouldn't be there. The fix is a cheap phonetic layer. Group names by how they sound, then re-rank that smaller set by spelling similarity that favors small edits and shared prefixes. It's fast, explainable, and slots in before any heavier re-ranker or profile lookup. Picture typing Stefan and getting Stephen, Stephen, and Stefan in the hits. Metaphone groups the sound-alikes into one bucket. A string score then orders the best matches. This improves recall for spoken variants, while remaining simple. The trade-offs are dialect differences and cases where different people map to the same code. We'll build a small pipeline, turn names into phonetic keys, fetch a compact candidate set, then rank that set by string similarity. The end result is a reusable baseline you can plug in before a profile join or a semantic stage. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's start by encoding one pair of spellings into a shared phonetic key. This snippet encodes one pronunciation variant pair with jellyfish.metaphone. Edit distance sees Stephen and Stephen as different character patterns, but name search often needs a pronunciation level signal first. The code sends both strings through jellyfish.metaphone, then compares query code and target code instead of comparing raw spelling. That gives us a cheap blocking key we can store and query before any re-ranking happens. The visible output shows the shared code, which is the first reason these names can become retrievable together. Now that single pair worked, we need a way to create lookups across a list without scanning everything each time. This example turns jellyfish.metaphone codes into a candidate index. Scanning every name with string similarity is simple, but it gets expensive and still misses sound-alike spellings if the first pass is too literal. The by-code dictionary stores each name under jellyfish.metaphone name, so the query only looks in one phonetic bucket. For Stefan, that bucket contains nearby pronunciations without touching Sarah, Sarah, or Xavier. The visible output shows a short candidate set, which is what lets later ranking focus on relevance instead of brute force standing. Buckets help, but they are intentionally broad. We need a clean way to order the few candidates we do retrieve. This code adds a second stage ranker with jellyfish-Jaro-Winkler similarity. A phonetic bucket is intentionally broad so it can contain useful variants and some names that only sound roughly similar. The scored list keeps each candidate with its string similarity to query, and ranked sorts by score first, then name for deterministic ties. That gives the retrieval system a clean split. Metaphone finds likely pronunciation variants, and Jaro-Winkler orders them for display. The visible output shows Stephen rising to the top, which matters because candidate generation alone is not a ranking strategy. Single token metaphone works for many cases, but real names have first and last parts. Matching only one token pulls in noise. This snippet moves from single tokens to full names using jellyfish.metaphone. Real name search usually has multiple parts, and matching only the first token can pull in too many unrelated records. The name key function splits a name and stores a tuple of metaphone codes, so first and last name pronunciation both participate in the lookup. That is still a compact teaching index, but it mirrors the blocking idea used before a larger search backend or vector retriever re-ranks candidates. The visible output shows two full name variants in the same bucket, which makes the candidate set more precise. Finally, we wrap the steps into a tiny search function you can call from other code. This example wraps the jellyfish flow into a tiny reusable search baseline. The search name function first uses name key to fetch only phonetic candidates from full index, then applies jellyfish.jaro-winkler similarity inside that small set. The limit parameter controls how many ranked matches are returned. Increasing it improves recall at the display layer, while decreasing it keeps the result tighter. In a hybrid or RAG retrieval system, this can sit before a richer profile lookup or after a lexical filter. The visible output shows the top pronunciation-aware match, which is the promised baseline working end-to-end. If you move this to production, map the toy list to your user table keys, and store the metaphone tuple as an indexed column. Then the phonetic bucket becomes an efficient pre-filter before any costly joins or profile reads. What this gives you: a fast pronunciation-aware candidate generator and a simple string-based re-ranker. Use it when spelling variants hurt recall and you need an explainable first pass. One caution: metaphone groups do lose dialect detail and can overcollapse distinct names. A practical next step is tuning the search name limit and measuring recall on your real customer list, so you know how many phonetic candidates to show before re-ranking. If short, practical IR helps, subscribe and watch the IR videos.